Well, good morning, everybody. Welcome to Ellensburg, Washington, USA. This is Nick Zentner speaking, live at 11:47 a.m. on Friday, March 1st, 2024. Welcome to you all. Looks like we're 5 by 5. Let me read the title slide to you. Electrifying CWU's heating system with geothermal energy. And our speaker today is Anthony Schoen from Spokane, Washington. Hope you enjoyed today's talk. If you're watching this in replay, you can skip ahead about 12 minutes to the beginning of the lecture. But right now, I'm going to get on camera and say hi to a few folks who are with us live. Happy March to you all. Welcome. Thank you for remembering to join us live. And if you're watching this in replay, you can skip ahead to the next chapter title, which is the beginning of Anthony's program. But this is a live stream, and there's many of you that are watching live, and you join us each time we do one of these Friday sessions. So thank you for joining us. I hope you enjoy the talk today. It will be different. This is not a geology talk, and Anthony is not a geologist. He's a mechanical engineer. But you will see, I think, the reason that he was invited to give this talk today. We have a full room, and people continue to come in, so we'll hope that the seats are available for everybody. Where are you viewing from today? Fabian, Alberta, Bethesda, Maryland. Good morning. Hi. Did you want to say anything?
I think you got it, probably.
Okay, yeah. Okay. I was surprised he had a little bit of time after the lecture to just hang out, it sounds like. He doesn't have a commitment until 3.
Okay.
So I guess I'll invite folks to stick around if they want to talk to him, and if there's enough people, then we would go get a burger or something. I don't know.
Okay,
we'll just,
yeah, that would be good.
Just improv that way.
Yeah, okay.
Yeah, thanks. I'm sorry. Where are you viewing from today? Springfield, Oregon, Marysville, Washington, Natchez. Pat from Natchez is in the room. Pat from Natchez made the trip up from the Yakima area today. Monterey Bay Aquarium. Hi, Don. Lakeville, Minnesota, Elma, Washington, Salt Lake City, Utah, Wilmington, Delaware, Boulder Creek, California, Kingsgate, Washington, Christchurch, New Zealand. Hello, Rob. Lincoln, California. Zoltan is still in Budapest. Still in Budapest. Smiley face. Nashville, Tennessee. Leamington Spa, UK. Dayton, Ohio. Kansas City, Missouri. Troutdale, Oregon. Tinley Park, Illinois. Pekka is in Finland. Nick is in the UK. Hello, Nick. Nice name you have there. Quilcene, Washington. Philomath, that's Kirk, in Philomath, Oregon. Can I ask one more time? Are we 5 by 5? As I swing you around and have you enjoy the room here. Thank you. That's Susan Kaspari talking to our speaker, Anthony. Bryce the Rock Licker with a smug look on his face. He has major amounts of senioritis happening right now. We're trying to drum it out of him, but he's out of control at the moment. He loves looking at himself on the screen. Should get a Bryce cam. We're 5 by 5. Thank you. In just a second, I will be getting Anthony's mic on him and double checking him as well. Let's say hi to a few more of you while we're waiting. I'm too relaxed at the moment, so great. Garrett, the Dutch Nadaal from the Netherlands. Hello, Garrett. Yeah, Bryce. Are you getting a master's degree in rock licking? Asks Brian. He's non-committal, Brian. He may or may not be getting a master's degree in rock licking. He has applied to oh boy, they're all talking about you. They support you, Bryce. All right. Bryce has an edge this morning. I can't explain it. Eric's in Southwest Virginia. Stan is in tropical Wisconsin. Hello, Nina from San Diego, California. Webb Lake, Wisconsin. John is in Media, Pennsylvania. LOLs across the board. Okay. All right. Thanks. Hey. I'm on YouTube right now, but how are you?
I'm well, yeah. Thank you. Yeah, thanks for putting this on my radar.
I'm glad you got the message.
Yeah.
I'm going to make a few announcements, and one of the announcements is this guy's got a spare hour after he gives this talk. So
Okay.
if you are excited about what you hear, you are certain, if you got time in your schedule, you can
Yeah.
stick around and we can just visit for as long
Great.
as you want.
Yeah, fantastic.
He's been involved in a lot of the buildings here, not just this project currently.
Oh, is that right?
So I didn't realize that. So
Oh, that's really cool.
are you still thinking?
Yeah,
Along those
absolutely,
lines?
Yeah. Yes, it's well, you know, it's power is like an essential component of any kind of economic development, progress, anything. Really.
Yes.
And you know, Kittitas County has kind of missed out on the dams,
Totally.
back in the day. And
Yes.
So, you know, is there an opportunity to do, you know, something that's, you know, low carbon and something like that to give us, you know, some kind of lower cost energy source of the, you know, this next generation of
Yep.
of renewables? Like,
Yep.
I think it's a really worth exploring. So.
Well,
Yeah.
a bonus is he's a Gonzaga grad. Is that
Oh,
where
is
you
that
went?
right? Yeah. Oh, that's
Okay. Very good. All right. Just keep chatting. I'm just going to come right in here. And I think we're
he
good.
live yet?
He's live right now.
Okay, let's
Yeah.
talk
Okay, cool.
I have questions.
Yeah, no, for sure. It was good to talk with you. Yeah.
Well, let's test your audio here a little bit. So, did your parents go to Gonzaga as well, did you say? Or
My mom
somewhere
did,
else?
yeah.
She did?
Mhm.
Okay.
Yeah.
I love that campus.
Mm-hmm.
What part of town did you grow up in?
I grew up mostly in the valley.
Okay, yeah,
And I live on the South Hill there now. Yeah.
nice.
Yeah. I love Spokane for sure. There's too many people hear that. Nobody should know about Spokane.
No, that's right.
Keep,
Well,
keep
no,
Spokane quiet.
I'm a huge fan, man, and I
No, I don't want to spread the word of how great it is.
got you.
Yeah,
I got you.
yeah.
Well, too late. It becomes obvious to a lot of people. I'm a huge John Stockton fan, so it's an inside joke when I say. Sometimes I don't say Spokane, I just say John Stockton's house, and they know what I'm talking about. Okay, viewers, are you able to hear our speaker today? Can you type Anthony 5x5, something like that? What's a little? Did you do more than one degree from Gonzaga, or just that mechanical engineering?
I got a minor in business, and I almost got a minor in math, but I figured engineering showed that I knew math enough. So
Okay.
yeah.
Good. Okay, they can hear you
Okay,
just
great,
fine.
perfect.
So we're good.
Okay.
So yeah, in just a second, I'll make a few announcements to everybody, and I think I'll say, if you're comfortable, not only can people come up after and visit with you, but if there's enough interested people, maybe we would just take you out for a little bite.
Yeah.
If you're up for that.
Happy to do that.
In fact, let me introduce you to a guy who went to Gonzaga. He lives in town, and he has a special interest in geothermal.
Yeah.
Just be aware that they can hear you if you
Okay.
don't. Yeah. Garrett, this is Anthony.
Come, Anthony.
Really nice to meet you.
Nice to meet you as well. Fellow Gonzaga
Yes,
alum.
Gonzaga. Yeah, I was
to hear.
2004.
Okay.
Yeah.
Great.
Yeah, I was a bio guy, but
I wish I had taken more biology.
Yeah.
More. Wish I had taken any biology.
yeah. Yeah, it was. I mean, it was good, but I ended up going to graduate school, and now I don't actually use any of it. I'm like renovating houses and participating in, as Nick may have mentioned, like a local economic development group. I chair a board called Centerfuse, and
Cool.
so we're just trying to look at broadly economic development. And one thing that's kind of always tickling around in the back of my mind is just the cost of power.
Mm-hmm.
And we're kind of next to Quincy and all those areas that have low power.
I'm sorry to interrupt.
Yeah.
Grit and polish.
Their cost of electricity is very, very, very low.
So he looks so familiar.
Just from a broad economic standpoint, like power feeds into the underlying, costs of all businesses, no matter what they are, and especially those, higher intensity businesses like manufacturing that, everybody's trying to get after these days. So, I kind of, just kind of keep my pulse on what's going on in green energy, and got into a little bit of the new enhanced geothermal, just through some podcasts and other things. I know that's coming online a little bit here and there, and so I was just talking to Nick the other day because I know his expertise is in geology.
Empty seats up front if you want them.
Just trying to poke his mind about is there anything around that's unique to this area, or a feature of this area that would make it amenable to some kind of one of these enhanced geothermal situations. And so but he basically said, well, we've got someone who's expert in that area of and coming on, and so I'm kind of excited to just hear your talk, and maybe we get a chance to chat.
Yeah, for sure. And I'm going to talk more specifically about the technology that's connecting, which is a heat pump.
Okay.
And I'm sure you've heard heat pumps in your work, so this may give you a little more insight of how they're working and other options. And geothermal may be the right answer, or it may be something else, but this will give you some of that background too. But yeah, let's definitely talk after.
Awesome.
Okay, and your name again?
Garrett.
Garrett. Okay, cool.
Oh,
Nice
the
to
good
meet
old
you.
days when everybody had a sense of humor.
Yeah, nobody else.
Okay. You're good with water and everything, Anthony?
Yep, got my waddle.
Okay, great. Okay, well, I'm about to start, and we'll just have you stand right here, and it'll be 5 minutes or less, and we'll turn it over to you.
Perfect.
Okay, thanks.
And I targeted this 45 minutes, so we have lots of time for Q&A. Is that right about where we want to be?
Yes, although there is a class at 1, but they just start as soon as we're done, kind of done in here. So don't feel
Well, we can
like
always
you have to rush.
exit and go talk out there too.
Exactly.
So.
Yeah.
Great.
Okay. All right. Okay, everybody, let's go ahead and get started. Thank you so much for coming today. We have plenty of new faces today, lots of new faces, and I hope that you feel comfortable here in this geology/physics building called Discovery Hall. And this building is one of the featured part of today's talk. In fact, many of the buildings on campus will be discussed today with our speaker, Anthony from Spokane. So especially those new to us, welcome. This is a series of noon talks that we do on Friday. Most of them are geology related. Today we have a mechanical engineer giving a talk, so it's a slightly different emphasis, but very pertinent to what's going on campus. So thank you for joining us today. I hope you enjoy it. We're broadcasting this on YouTube live, so that's why you'll see some funky stuff going on occasionally with some cameras. Pay no attention to it. We're all in the same room, and we're listening to the speaker talk about geothermal energy here in Ellensburg, Washington. Great. A couple of quick announcements. This will be about an hour or so, and when we are done, in other words, you'll have a chance to ask some questions and answers. You do the questions. Anthony will give you the answers. When we're done with that, there's 2 more opportunities for you if you are still in the mood. Upstairs in room 206, there is a series of alumni of this geology program who will be speaking to many of our graduating seniors. And the public is invited to do that. So room 206, if you want to hear about some of our best graduates and them coming back and giving some tips on the real world out there. There's another opportunity right after this lecture, and it's sitting in on a thesis defense, a master's thesis defense. Mandy, what room are you speaking in?
116.
116, so just down the hall on this floor. Are people welcome to come if they want to listen? Okay, what else are you going to say at that point? Right, very good. So yes, Mandy will be speaking, and you're welcome to listen to that as well. Third option for you, if neither of those appeal to you, and you want to stick around and talk to Anthony more about geothermal stuff, feel free after our question and answer to just come up and we'll have a small group continuing to talk. Anthony has room in his schedule for the next hour, hour and a half after 1 o'clock. So if there's enough of you wanting to stick around and do that, we'll just walk across the street and find some food someplace and just keep the discussion going. So you got 3 options. I guess the 4th is getting the hell out of here and going back to your normal life. But those are your 4 options. Great. This is the last Friday at noon talk of the quarter. But when we start the spring quarter, the last Friday of March, I don't have the date in the top of my head, Harold Tobin from the University of Washington will be here giving an earthquake talk hosted by Tim Melbourne in the Panga Lab. So I will make sure that you know about that and the rest of our spring talks organized by Hannah Shamlou and myself. Okay, anybody want to say anything else, announcement-wise or clarification? We good? I can feel that you're ready for the talk, and I am too. Our speaker is a Spokane native, born and raised in Spokane, went to University High School, and went to Gonzaga University, mechanical engineer. And Anthony has been intimately involved in many of the newish buildings on campus, including the project that's going on right now. Would you please help me welcome Anthony Schoen and his talk today, Electrifying CWU's Heating System with Geothermal Energy. Anthony.
Thank you, Nick, and thank you, everybody, for having me. So as Nick mentioned, I'm Anthony Schoen. I'm a principal at MW Engineers. I'm a mechanical engineer by trade and am absolutely happy to be here today. What our MW Engineers is a firm in Spokane, Washington, single office. We're a little over 60 mechanical and electrical engineers, and we do everything inside a building. So the lighting, the HVAC, the water systems. I specifically design HVAC systems, so heating and cooling and everything that connects to that. We've been very fortunate to work on CWU's campus for over 20 years now. And this new geothermal building
Here it
is one of the many buildings that we've had the pleasure to do. You're also probably very familiar with another building that we've worked on, and that's Discovery Hall, the building we're all in today. So this is actually our 40th year in business, and happy to be able to walk through this. So North Academic, the geothermal plant is part of a larger story, the North Academic Complex. I'm sure a lot of you have seen construction started at the north end of campus, and we'll kind of orient you a little more about where all this is happening. But the geothermal plant kind of came out of that project and has really blossomed into something tremendous. And I want to kind of focus today to talk about the macro level of why is this project happening on campus, and then start to dive into more of the specifics, the micro level of what is actually happening in this building, what is the technology we're using, and specifically we're using something called a 6-pipe heat pump, and that's what's actually making this all-electric heating energy. So you may ask, some of you may know, but some of you may be wondering, why are we here today? Well, currently most of CWU's campus is heated by fossil fuel fired steam boilers located at the central steam plant. And so those steam boilers make steam, which sends steam out to all the buildings and heat the buildings. Well, CWU has been very interested in how do they lower their carbon emissions, and they're accomplishing that by this project, which is using this 6-pipe heat pump to create all electric heating energy. And so I want to focus on, I have some learning objectives today that we're going to kind of walk through. And I want to make sure, like I said, I want to help everybody understand why this is happening, what's important, and what are the other facets of this geothermal plant that impact the campus at large. And so the first is understanding the total carbon or the total life whole life carbon of a building. So I'm sure a lot of you have heard carbon emissions. What does that actually mean, and what is factored into the total carbon or whole life carbon of a building? Next, why is energy use important in buildings? Obviously, if we use less energy, your utility bill's less, but what else does it mean? Why else is this important? We're all a part of Washington State, and CWU being a state campus, what Washington State's goals are ultimately impact decisions made on campus and how things are funded. So that we're going to talk about that a bit. And then CWU. So this project is obviously a tremendous step forward in the decarbonization of CWU's campus. But what has CWU been doing for the last several decades, and what do the next several decades look like for the campus? Then we're going to start diving into what everybody's really interested in, and that's the GeoEco plant. The GeoEco plant is the building itself that houses this 6-pipe heat pump. And then finally, what is at the heart of this system? And at the heart of this system is that 6-pipe heat pump. So what is a heat pump? I will make sure we all know I am not a hydrogeologist, so we'll talk very loosely about the ground connection, but we'll make sure we understand how the systems are using the interface with the ground most specifically. So if we start with understanding the total carbon or that whole life carbon of a building, it's really two different factors or components that equal the total carbon of a building. And the first is embodied carbon. So embodied carbon is all of the carbon associated with making the materials, with building the building, so mining the ore, creating the steel, erecting the building. You'll notice on this graph, so this is a very kind of diagrammatic chart of that total carbon of a building. The x-axis is time, the y-axis is carbon footprint. You'll notice on the very left there's a construction phase. The construction phase is identifying that as construction happens, that embodied carbon increases with the construction of the building. Once the building's occupied, so during the occupancy phase, that kind of stabilizes. That's not to say that if buildings are renovated or maintained, there can be additional increases in embodied carbon. From that point of occupancy on, we now look more at operational carbon. So the operational carbon is what carbon emissions are associated with heating a building, with the lights in a building, with all of the systems required to actually run the building. And why that's important is because the most obvious culprit of operational carbon is the heating system. So think of your house maybe. You've got a gas-fired furnace. Every time you turn on your furnace, it burns gas to heat your house. Well, that's very true to buildings like this on campus. When we need to heat some of the buildings connected to the steam plant, well, you have to turn on those steam boilers, create the steam. The steam is distributed to the buildings, and there's losses associated with that distribution, which reduce efficiencies. So that's what this fuel-fired building line represents. So you're using fossil fuels to actually heat and operate your building. Then we can transition to all-electric buildings. So buildings that use electricity. That could be electric radiant heaters, it could be an electric boiler, an electric water heater. Those can have the opportunity to use less or have less operational carbon associated with them, but it really depends on how the electricity is generated. If we're generating the electricity with a coal plant, well, that may not be super clean power. Washington State is very fortunate that we have very, very clean power as a whole, and we'll talk a little bit more about what Washington's doing here in a minute. A net zero building is kind of a gold standard. You're producing as much energy at your building as you're using. And you're doing that through solar panels, windmills. You're trying to make as much as you need to use. And so that's where you have no operational carbon associated with the operation of the building. And then finally, a renewable building. You make more on site than you actually use. So that's the dream of really having an impact of lowering the total carbon of your building. So we now understand why, what is this carbon, but what does carbon have to do with the rest of the building, and how does it relate to the building? So understanding how we use energy, obviously the more energy we use, the more heating energy we use in a building, the less efficient a building is, the more energy we need to make, which can have more of that operational carbon. So I want to make sure we're all understanding a common term that we use in this industry, and it's called Energy Use Index, or EUI. So Energy Use Index is the measurement of the amount of energy used in a building. It's a tool to compare different buildings. So it's the units used are KBTU per square foot per year. So it looks on a per square foot basis per year. And it takes into account all of the different metrics, or all of the different energy using systems in the building. The lights, the fans, the heating, the cooling, how efficient the envelope is. Do you have really good windows? What kind of climate zone you're in? Are you in the Arctic? Are you in somewhere that has really hot summers? And then any on-site renewable energy. You can think of this kind of like miles per gallon in a car. If you have a sedan versus an old truck that's towing, and the sedan's used for commuting, well, both take into account the efficiency of the tires, the air conditioning, but ultimately using those two to compare one another may not be a useful tool. Looking at a truck that's towing something versus a new sedan that's driving somewhere, that doesn't tell you much about the efficiency of the car. If you look at a new truck versus an old truck, what you can learn from the mile per gallon comparison is that the new truck may have a better mile per gallon rating, and you can understand why the old truck isn't running as efficiently. So same thing's true for EUI. If we look at the EUI for multiple buildings, like a science building versus your house, that's probably not a very fair comparison. Science buildings have a lot of environmental conditions to protect people from the chemicals or rock crushing or processes happening in the building. And this is also true for comparing to things like North Academic. And I'm telling you all this because I want to look at a few examples across campus of just how is energy used. And again, this is all trying to help understand what this geothermal plant is ultimately doing. So we're looking at three different buildings on campus. I'm sure you're familiar with a lot of these. Green is Science 1, blue is Discovery Hall, orange is the new North Academic Complex that's under construction. So we've broken this down into 5 different energy categories: heating, cooling, fans, pumps, domestic hot water, lighting, and receptacles. So what's really interesting about this is you can see the big spread of energy differences between buildings. So first off, we can see that North Academic uses less than the science buildings. Like I said, that should be obvious. Science buildings can run 24/7. They're protecting the environment. They have different needs. You can shut off a classroom office building in the evenings, at night. You just don't have to run it as much. It also doesn't have as many demands as the processes that happen in science buildings. But what's really interesting here is if we focus just on the heating, and remember, Science 1 is connected to the central steam plant. So it uses fossil fuels to heat the building. Science 1, which opened in the early 2000s, versus Discovery Hall that we're in now, which opened in 2016-ish, uses about 3.5–4 times as much energy to heat the building. And that ultimately means more energy at the central plant. And this is actually a great comparison because it's changes in technology, there's opportunities that can be identified of how you lower that number. The lower we get that EUI, the less energy we need to make in a geothermal plant or at the steam plant, the less carbon emissions associated with the building. And Science 1 is actually on CWU's radar, and they're very aware of this and looking to lower the energy use of that building. And not just in heating, but across the board to bring that EUI down. So before we move on, I want to ask, does anybody know what the most efficient, energy efficient, and lowest carbon emission system is? I'll take the crickets as, okay. Great idea, but it's actually the system that's off. So the most energy efficient system is one that you don't have to use. It is a total trick question, but when we're designing buildings, we really have to think about how do we design the building to just turn off as much as we can, or turn off systems we don't want to use. And that can be a great thermal envelope. There are systems that need to run, and so the next step, like ventilation in a science building, the next step is how do we make those systems that have to run as efficient as possible. So it's a multi-step process in trying to identify the most efficient way to run a building. So now that we understand energy use, the importance of it, carbon emissions, let's look at what Washington State's doing. What are their energy and carbon goals? And quite simply put, Washington State's carbon goals, or goals in general, are to be a net zero carbon state. They want to reduce carbon emissions as much as they possibly can. And they're doing that through quite a few different ways, but first it's helpful to understand how is the state how are the carbon emissions in the state accounted for? So the left pie chart shows a simple breakup of where carbon emissions are largely associated with. You'll notice that buildings and transportation are the two largest contributors to carbon emissions in Washington, followed closely by electricity generation. And Washington is addressing both transportation and electricity generation separately, and we'll talk about that a little more in a minute. But the more interesting graph to me is the bar chart on the right. And you'll see that from 1990 to 2015, buildings actually had a 51% increase in carbon emissions associated with them. So they have had they've kind of gone the wrong direction. So buildings are really important to the state to help achieve their goals of lowering carbon emissions. So how are they doing that? We're going to look at a very abbreviated timeline. And this timeline goes many years in the past and has many more milestones, but I kind of want to hit a few of the big points in the next 30 years that Washington's going to be implementing. So the first is energy code is going to largely restrict the use of fossil fuels in Washington this year. So the last 20 years there have been many cycles of the energy code to lower energy use in buildings, to make buildings just more efficient, to look at systems that use energy better, and this is going to be a major step towards lowering carbon emissions associated with buildings. Next, we have three major milestones as part of the Clean Energy Transformation Act, or CETA, and that's where Washington is restricting the use of fossil fuels in electricity generation. So 2025, no coal for electricity generation, 2030, carbon neutral electricity generation, 2045, fossil fuel-free electricity generation. So that's addressing, if we're plugging in an electric building, that we're not plugging it into a very dirty energy source. Something that's not on here is 2035. Washington's is going to require all new vehicles are zero emission or using electricity as a primary source for commuting, and that's addressing the transportation piece. Starting in 26 through 2028, there's something coming into play that mandates that buildings, commercial buildings over 50,000 square feet, have EUIs that align with similar buildings or requirements of similar buildings. So this science building uses no more than this benchmarked requirement. So that's addressing all new and existing buildings because as you noticed from 1990 to 2015, a lot of buildings kind of fall out of calibration, and by falling out of calibration, they can use more energy. So this is helping address those older buildings that aren't operating as efficiently and making sure new buildings are operating efficiently. And then finally, 2050 is that ultimate end goal of being a net zero carbon state. So Washington State obviously has a lot of influence on all of what everybody does, including Central, but Central has also identified some very specific sustainability goals as a campus, and we can see that, one, by the geothermal plant, but I want to take a step back and recognize what CWU has done more globally. And the biggest thing that CWU has done is they've been a forward-thinking university. You can see that in buildings that they've done for many decades, including this, when we compare Discovery Hall to Science One, at how much less energy this building was using than that. And this is true especially with this geothermal system. I know I'm talking a lot about this geothermal system. We'll get into that very soon, I promise. But that is a major step as a university, that they are the first university, state university in Washington State to do a geothermal system at this scale. So the other thing that CWU has done is they've actually made are in a draft form of the their climate change action plan. And this climate change action plan is what is going to be used as a tool to make all decisions moving forward on campus. The overarching goal of this climate change action plan is really aligning with the state in many ways of a net zero carbon campus. And what this plan does is it establishes measurable milestones that they can continually check in on to make sure that all of their decisions are keeping them on track for that ultimate goal. And I'll have something more later on in this so people can read this entire plan and provide comments. So what else CWU has done as a university? So this is North Academic, the North Academic Complex. This is the bigger part of the geothermal plant story. This is the new building that's going up at the north end of campus. This is where the geothermal kind of stemmed out of. And you'll notice down here in the right of the image, that's the geothermal plant that's kitty corner across the street from North Academic. And so North Academic has a tremendous story because, as we talked about, lowering your energy use means less energy is needed to be made to service the building. And so early on at the inception of this project, the team identified how can we use less energy in this building so we don't need to make as much. And we did this by looking at, we developed what I'd like to call an energy roadmap. And this roadmap has a bunch of different colors on it. Don't need to worry about reading them. Really what these are, what I call energy buckets. So like the red is identifying the heating energy, and blue is cooling energy. The yellow on the top is the domestic hot water. And what this tool helps us do is we start over here at the left and say, okay, well, the energy code says we can have a building that has this kind of EUI. And this building, the baseline, is a building that is really what CWU likes to use. So you notice already CWU has energy systems and is doing things on campus that is significantly better than the energy code. So they're already making these steps. But the campus was interested, how do we take this a step further? How can we lower the energy use further? And each of these alternates, that's what ALT stands for, are looking at different things that happen in the building. Do we put a better envelope in? Are we using a more efficient energy recovery system? How can we use domestic hot water better? And in each of these iterations, we develop an energy model that looks at what that energy change is by making change into the building or the energy system. We also look at the costs associated with each of these because when you get to here, alternate 5, you see we've lowered the EUI of the building, and now we're looking at offsetting the energy with renewable energy on site. And that's, in this case, solar panels. So putting solar panels on the roof. This has a cost to it. It lowers the overall energy use of the building, but it has a cost. And so through this process, we continue to identify different options. And one of the major changes from alternate 8 to 9 was the implementation of a geothermal system. And so this is where we showed this is an option to get to net zero. And we may blend a lot of these options ultimately when we evaluate the overall cost of it. And CWU is very in touch with being fiscally responsible. They are using state dollars. They also need to be able to operate and maintain these buildings. So where did we end up? Well, we obviously ended up with a geothermal system, but I have 2 bars here. The left bar, I mentioned in 2026, the state is going to start requiring that buildings meet an EUI. The state allows for this type of building an EUI of about 112. from the bottom of the blue to the top of the orange is about the total EUI of North Academic, and this orange is with the solar panels on the roof. The expected energy use is just this blue bar of North Academic, which the EUI of North Academic is expected to be about 10. So over a 90% reduction in energy use, and this is attributed to the design team identifying methods to lower the energy use as a whole, and also finding ways to then offset. So how does this all tie into the GeoEco plant? So the GeoEco plant is obviously why we're all here, and that's really the macro understanding of why this was all important, why this is happening on campus. So the GeoEco plant, let's kind of orient everybody here and online of where this is happening. So we're here in Discovery Hall. Directly north of us is the North Academic site. Some of you have had the chance to tour that today. I hope you all got to look out there, or you'll see the fencing when you're walking around campus. Kitty corner to North Academic is the GeoEco plant site, and it's a very, very intentional site on the corner of D. Nicholson Boulevard and Walnut, and that's because there's a lot of student and faculty traffic around that corner, but it's also a very public corner to the community. It's not buried or tucked away far away from the eyes of the community or the public. It's placed in a spot that encourages people to go and learn about it, to interact with the building. It's really intended to be a showcase and a demonstration. We also have the extraction well, which is just west of the geothermal plant, and then the injection well. And we'll talk more about what these do, but the extraction wells where we're pulling water from the aquifer, and the injection wells where we're reintroducing it or putting it back into the aquifer. So you've seen some pictures of what this geothermal plant looks like from the outside. Well, if we just peel back the shell of the building and look at what's inside, so this is all the parts and pieces of this system that makes and moves the water around, makes it hot, makes it cold. And so we've color-coded the pipes to help kind of identify which systems are which. But at the heart of the system, you'll see the 6-pipe heat pumps, or those 2 big boxes in the middle. Those are actually what are making the hot water and the cold water. And then from there, they're moved throughout campus through large piping distribution systems. The dark red pipe is the hot heating water, so that's the water that goes out to a building and heats the building. It releases energy into the building, and the water comes back at a lower temperature in the orange pipe and is reheated with these 6-pipe heat pumps. The blue pipe is cold water, so it leaves the building, goes out and cools buildings. Energy is added to that cold water pipe and comes back warmer, and that's the light blue pipe, and it's recooled through the heat pumps. And then the green pipes are the groundwater pipe. So that's what's actually interfacing with the aquifer. Some other really important pieces of equipment here, you can see in the back corner is a groundwater heat exchanger. So something to note about this geothermal system is it's using the groundwater, or the aquifer water, and it comes into this building. It's not used, it's not consumed. So it comes into the building and then it's re-injected. There is no consumption of this water. The groundwater is only an energy exchange, so we trade energy with it. And it's actually even protected through this heat exchanger. This heat exchanger has plates, and we'll look at an exploded view of this. It has a physical barrier between the water in the building and the groundwater, so there's no contamination of the groundwater. So there's no interface with that groundwater with actually the fluids in the plant. A buffer tank, so the buffer tank is a big tank that has a lot of additional volume, and what that additional volume does is it keeps equipment from having to turn on and turn off and turn on and turn off. The more volume you have in a system, the less those things have to cycle, and that cycling can really be detrimental to equipment life. These pumps, the pumps are what actually move the fluid. So it moves the fluid around campus to all the buildings, back to the GeoEco plant, and then through all of this equipment. And you can see the pumps around the perimeter. The air dirt separator is what's suspended in the air, and that's pulling dirt out of the water. Dirt can clog things, and it's pulling air out of the system. Air can be really damaging to water systems. The expansion tank, you can kind of read it down there, is the tank here. And what that's doing is as you heat up and cool down water, it expands and it contracts. And there has to be somewhere for that expansion contraction to go, or you can pop pipes and blow holes in things. Not really good. So this is a tank that's filled with air and has a medium that separates the water from the air to allow somewhere for that to expand. So this is an actual picture of the 6-pipe heat pump. You'll notice the person at the end to give you a sense of scale of the piece of equipment. There's 2 of these, so they're very large pieces of equipment. They're very large. And you'll see there's 4 pipes coming out the end. There's another 4 going out the back. I mentioned this is a 6-pipe heat pump. So there's 3 different water streams. There's the groundwater, the heating water, and the cooling water. And that's where these pipes are going to connect around the ends. This is a picture and a diagram of the heat exchanger, that groundwater heat exchanger. The left picture is what it looks like, what you'll actually see in the GeoEco plant. And this right picture is an exploded version that kind of shows you the composition of these heat exchangers. And this is a plate and frame heat exchanger. You'll notice there's blue and red colors between the different plates. These represent the 2 different water streams. There's the water stream in the GeoEco plant and then the groundwater. And you can see there's an actual physical barrier, that steel plate between these, protecting that groundwater. So now we're going to do a fly-through video of the GeoEco plant. So you'll notice that the roof is covered in solar panels. The landscaping is very encouraging to get people to walk up to the glass window looking in. But let's actually go inside of the plant. So on either side of us here are those 6-pipe heat pumps. And then we've got all the different heating water and chill water pipes. These are the pumps, so these are what are moving that fluid around campus. This is that heat exchanger we were talking about. Those 2 things to our left are filters. Those actually pull sediment out of the water from the ground to make sure it doesn't clog equipment. These are more of those buffer tanks, the extra volume in the system. We've got the heating and cooling ductwork above us, more pumps moving the chilled water around campus. And this is one of the several expansion tanks in the building for that expansion contraction. So it's all organized in a way, and this color coding is to help you see what the different systems are. This is going to look a little different when it's done, but it's going to be organized and drawn out to show everybody what's happening so you can learn about it. Something else really important is the orange up here. Some of the pictures we see show it a little better, but this is a mass timber building. So it uses renewable, highly renewable wood in the construction of this. And why that was done is because the energy systems were installed or designed to lower that operational carbon, but the construction materials of the building were also heavily looked at to lower that embodied carbon associated with the building. So this building is anticipated to achieve net zero energy and net zero carbon awards. So it was as a whole looked at to make sure we're not just addressing one thing, we're addressing the whole meal deal. So now we've looked at what's holding this all, what are the systems connected to it. Now let's look at the heat pump. what is a heat pump? What is this 6-pipe heat pump we keep talking about? And how does it interact with the ground? So this is an important diagram because to understand a heat pump, we have to understand something called the refrigeration cycle. And to understand the refrigeration cycle, we need to understand how latent heat works. So, and I know a lot of you are probably familiar with this, but it's really critical. So moving from, we're looking at a unit of measurement here called the calorie. Calorie is defined as one moving 1 gram of water, of liquid water, 1 degree Celsius. And why that's important, if we look at the diagram in the middle, moving from 0 degrees Celsius to 100 degrees Celsius requires 100 calories. Moving from solid or ice, solid H2O, to liquid water requires the addition of 80 calories. Moving from liquid water to water vapor requires the addition of 540 calories. So a tremendous amount of energy is required to be put into liquid water to just move from liquid to vapor. And that's true moving from vapor back to liquid, there's the removal or release of energy. And this phase change and the energy associated with the phase change is what something called the refrigeration cycle is largely dependent on. So the refrigeration cycle, you're probably all familiar with a refrigerator. Refrigerator, believe it or not, does use the refrigeration cycle. And how your refrigerator works is it cools the inside of your refrigerator, and then it rejects it. What it's doing is it's moving the energy from inside your refrigerator to the room. It's rejecting it to the room, and it does that through the refrigeration cycle. So how the refrigeration cycle works, if we start just to the left of the compressor where it says low pressure gas, so entering the compressor we have low pressure, low temperature gas. The compressor requires power in, so this is where work is happening, and we're compressing this gas, and coming out of the compressor is a high pressure, high temperature gas. So we've increased the pressure. The high pressure, high temperature gas now goes to the condenser. The condenser would be on the outside of your refrigerator, or if you have air conditioning at your house, it's what everybody thinks is the air conditioner outside. That's really a condenser. So this gas goes to the condenser, and through the condenser, the high pressure, high temperature gas condenses into a high pressure liquid. So we've changed phases, and through that phase change, we've released or removed energy from this refrigerant. And a refrigerant has similar properties to liquid water. It can change phases. From there, we take this high pressure liquid through an expansion valve. The liquid expands and comes out as a low pressure liquid. The low pressure liquid then goes through the evaporator. The evaporator would be inside your refrigerator or something inside your furnace for the air conditioner, and it's actually taking energy from the space and changing that low pressure liquid into a low pressure gas. So that phase change is capturing that energy. And so this is how the refrigeration cycle works. And why this is important is this is essentially how a heat pump works. A heat pump can do this, but it can do it in reverse. So it reverses this whole cycle. So imagine if your refrigerator could warm up the inside of your refrigerator and cool off the room it's in. That's how a heat pump works. So there's effectively 2 types of heat pumps, and there's many subcategories of each, but there's air source heat pumps and there's water source heat pumps. Air source heat pumps, as we have, there's a diagram on the left, they're exchanging energy with air to air, so kind of like your refrigerator, moving energy from the air inside the refrigerator to the air inside the room. The diagram on the left shows that this can be done throughout the year. So in the winter, you're moving energy from the air outside. So the cold air, you're trying to pull energy out of that, and you're trying to move it inside your house or your building to warm up the building. You can imagine that can be very challenging when it gets really cold. There's not as much energy in the outside air to bring in. And then similarly, in the summer, you're now moving energy in the warm inside space into the hot outside space. And the hotter it gets outside, the more difficult it is to reject that energy to the outside air. So there are challenges with the air source heat pump, but they're very navigable, but it is something to be aware of. Then there's something called a water source heat pump. There's a lot of different styles, but we're going to focus today on a water-to-water heat pump, and more specifically an open loop ground source heat pump. So this is the type of system that's actually in the GeoEco plant. And how this works is, unlike the air-to-air, we still use the refrigeration cycle in both directions, but we're trading energy from water to a water source. And we do that through the 6 pipes, or the 3 different methods. We can either make hot water and heat buildings, we can make cold water and cool buildings, or we can trade energy with the aquifer. And that's one huge advantage CWU has is the Ellensburg aquifer under us is a giant heat sink that allows us to exchange energy with the earth. The whole earth is what we call a heat sink, and that's where there's a high stability of temperature throughout the earth. And the fluid is one way to pull out very stable groundwater temperatures and trade energy with it and re-inject it back into the earth. And so this is how we're using this open loop ground source heat pump. So you may ask yourself, well, why a heat pump? Why are we using a heat pump? Well, why not an electric water heater or an electric boiler? Well, it really comes down to the efficiency. So I'm sure everybody's familiar with an electric stove top that you cook on. How that works is it brings electricity in and it uses resistance to turn that electricity to heat. And electric resistance heat is 100% efficient effectively. It's energy in equals energy out. Sounds great, but what if we could do better? A heat pump uses an efficiency measurement called coefficient of performance, or COP, and it's measured in the energy output, so how much energy you get out of this, over the energy input. And believe it or not, heat pumps can actually operate in excess of 800% efficiency. And it's because they're not creating energy. We're creating the energy here. A heat pump is trading energy. So think about it as an energy trader. We're trading it with the aquifer, we're trading it between air streams, whether that's your refrigerator from in the space, the outside of space, or more globally between buildings. So the more energy out of the system we can use, and the less energy we put into it, the more efficient that gets. If we're trading energy with the aquifer, we may be 200 or 300 or 400% efficient. So identifying scenarios where we can trade energy between buildings is the best way to do it. And so we're going to look at an example. We're going to look at, this is Central Washington's campus. We've got all the buildings kind of extruded out to kind of give you a sense of the campus. We've got the Geo-Eco plant up north, North Academic. We're going to pull this away. We had talked about that this heating water and chill water is distributed throughout campus. It's distributed throughout campus via piping. So there's pipes that are connected to a lot of different buildings on campus, and they're multiple water systems. So the first one we're going to look at is the heating water. So you'll notice that we've got a handful of buildings connected to the heating water piping. We're down here in Discovery Hall. We've got Samuelson Health Science. Up at the top, we've got North Academic and the Geo-Eco plant. So those are all the buildings that are or are going to be connected to this heating water piping system. We've also got a chilled water piping system that's significantly more extensive because it's older. The heating water piping system, about 10 years old. The chill water system is been around for a lot longer. It actually connects to almost every building on campus. So now let's kind of pan around, start at the north end of campus looking south. We've turned on both the heating water piping and the chilled water piping. And remember, both the heating water and the chilled water are connected to the Geo-Eco plant. So the Geo-Eco plant is connected to almost every building on campus. Well, let's look at a scenario where one building isn't heating and one building isn't cooling. So Discovery Hall needs to be heated, North Academic needs to be cooled. This is a very real scenario. There are times in the middle of summer where a science building needs heat, and it could be for hand washing, but it does happen for other reasons in science buildings. And North Academic, it's hot out, there's students in all the rooms, they need cooling. So let's kind of zoom in here. If we look at what if we send cold water to North Academic. So cold water, it comes back warmer and needs to be recooled at the plant. We send hot water to Discovery Hall and it comes back a little cooler and needs to be rewarmed. And then we trade that energy using that 6-pipe heat pump. So we're moving that energy from Discovery Hall to North Academic and vice versa. So we can move this energy between buildings and use that 6-pipe heat pump to do that exchanging. So this is the best way this system works. This system is optimized to use energy trading across campus as much as it can. And then when there aren't these simultaneous loads, or we have more heating needs or more cooling needs, then it can exchange energy with the ground, with that groundwater, with the aquifer. So we have 5 buildings connected to, or a handful, 5 buildings connected to the GeoEco plant that can use this energy. Well, this is a simple diagram of the entire campus. This is all the buildings on campus. The blue lines are the chilled water, the orange lines are the heating water. And then you'll notice these red circles. So at the very top, you'll see the GeoEco plant and then North Academic. So this is representing the area that the GeoEco plant is intended to serve. And you notice it is connected to other areas of the campus. So the plan long term is to continue to build out this heating water network to continue to connect to more and more of these buildings on campus and build other GeoEco plants around the campus, which are these red circles, to ultimately connect as much of and the whole campus on all electric, renewable energy. So this is the long-term goal of how CWU is going to kind of continue to move forward and connect more and more buildings using geothermal energy. So that was a lot of information. There was a lot of talk about why and how and getting into the specifics. I would personally like to thank all of you and the faculty for having me. And I just can't express how excited I am, and I hope all of you are, that this is happening on your campus. This is tremendous, and it's tremendously exciting because it is a leader in Washington State. And I'm happy to stick around and answer questions for as long as people need. So with that, I'll turn it over and it's open to questions.
Questions for Anthony, and Anthony is going to do his best to remember to repeat the question so that the home folks can hear the question.
Okay.
Please.
Yeah.
Anthony, great presentation.
Thanks.
I was interested to what component energy storage is a factor in this. In other words, in the wintertime, you're taking heat out of that deep aquifer, using it to heat the buildings, and then in the summertime, heat is going to be put back in there. Is there a component of seasonal energy exchange, or is it too small scale and it just mostly dissipates over those time scales?
And are you specifically talking about the aquifer or more globally?
Well, this project in particular.
Yeah, so the question is, how are we addressing energy storage in this? So the campus already has a 1 million gallon chilled water storage tank. So there is a place to store cooling energy in the summer. The heating storage, this project identified some small scale storage, but there are opportunities in the future to identify larger scale storage to charge these tanks when you maybe don't need as much heating energy and then use it throughout the day. I think that's what you're after?
Well, more I was interested in energy storage within the aquifer.
Oh, energy, okay. And so your question with energy storage in the aquifer, and this is where I'm going to answer what I know, but again, not a hydrogeologist, so there will be a talk later about the hydrogeology. So the aquifer is a moving body of water. It's kind of like an underground river, and the design of where these injection and extraction wells are placed is very intentional, so that you pull water out at a spot that is not impacted by where you put it back in. So that movement moves the temperature and then allows the earth as a heat sink to kind of realign the temperature of the groundwater with the earth at large. So the placement of the wells is making sure we're not reliant on recharging the aquifer. Does that answer your question? Okay. Yeah, so
Is that, do you lose any efficiency by bringing that up and showcasing it?
yeah, so the question is, if this was a non-educational institution, would all the piping we see in the GeoEco plant normally be above ground or below ground? usually it's hidden in a big concrete box at the back of campus where nobody sees it. That's no joke. There is the central steam plant. You probably kind of see it. It has all the same kind of piping that you would see above the ground. So all of this does happen above the ground. There is a tremendous amount of below grade infrastructure to connect that building to the wells and then connect the building, that building to the buildings on campus. So there is a lot of pipe that goes below ground. What's special about this project is that it's placed in a building and with glass walls looking in, and just a lot of attention to organization of the systems so that it's easy to see and understand and learn what's happening. That's the special piece here, is the organization and attention to detail of how it's installed versus like, nobody ever sees that. Nobody cares what it looks like. Yeah. Huh? Yeah.
I was just curious about what the range of temperatures are that you could work with from the aquifer. I know Delano had said it's at 65 degrees, but just how cool or how warm an aquifer could be to still be appropriate for this use. And then just the second part of the question is when you guys do drill the test well, are there certain things that you're concerned about that you could end up finding in that would create challenges for you?
For sure. So two-part question. First question is what temperature ranges are acceptable for geothermal, and two, what could we find with the test well that could be problematic? So the first, I would say the more important piece than temperature is actually the abundance of water, that it's there and you can take enough of it to use in your systems. And when I say take enough of it, remember it's non-consumptive, take and re-inject, but places that have non-porous geology that doesn't allow that flow of water, that's where the open loop ground source heat pump is challenging. Advantages you have with the colder the temperature of the water, you can actually make or just use it for cooling in your building and use no compressors. So there's advantages to colder water. Warmer water is totally acceptable to use in the system. I can't think of a scenario where you couldn't use in this. And then obviously there's scenarios, this type of geothermal is not to be confused with what you see in Iceland or Yellowstone, where you're harnessing steam pockets or boiling mud. Or so I think the whole spectrum has opportunities. It may be a different piece of equipment at the heart of the system, but it could be used in different ways. We're doing looking at another geothermal project where the groundwater is so cold, we just run it through the building for cooling without any compressors or any of that work in. So it's just pulling the water out to cool the building. So there's all sorts of uses for geothermal. And then the second part, don't forget that. The second part, what could we find with the test well? The biggest one is, well, we hope we find water. That's just totally frank. If we find water, then it becomes more of a how many wells do we need to get the amount of water we need? If it produces 100 gallons per minute versus 10,000 gallons per minute, those are totally different scenarios of how many do we need and what can we produce. So it's going to be very telling. And this is where the hydrogeology is really important. The design of the well itself. There's different casings and material used to help filter out material, because what you don't want to have happen is you don't want sediment and debris to clog up your well, and then you have no water to provide the heating and cooling. So understanding the layers we go through is going to be tremendously important in the well design. In the back.
Andy, you did a great job of explaining the science and how to apply it and the impressive efficiencies. On the financial side of it, the cost for your firm to design it, the infrastructure, the non-recurring cost,
Mm-hmm.
how long does it take for those curves to cross or break even? In other words, if you didn't have this geothermal plant versus having it, how long does it take for those costs to get into this?
Yeah, so I'm going to say it is a little complicated because this is a central utility plant that does not only service North Academic. So if we look at the cost of this plant for just this one building, it doesn't make sense because this plant is designed to serve about 500,000 square feet. So the North Academic building is about 106,000 square feet. So just this building is 119,000 square feet. So just frame a reference of it's set up to connect to many more buildings. So the first cost for this building is higher, but then as we build more buildings and connect to it, the cost of those future buildings is lower because the infrastructure is in place. The other part of it is it depends on the metrics used to evaluate. So if you're accounting for, and Washington State has tools to do this, if you're accounting for the social costs of carbon associated with burning natural gas, because natural gas may be at a lower price point right now, but there is a cost to burning fossil fuels. The costs become much more in alignment, and the ROI, or return on your investment, the payback period, comes down significantly. So I can't say it's a hard and fast, oh, it's 3 years or it's 28 years. This is an investment in the university that is forward thinking of reducing carbon emissions, addressing the cost of that carbon, and also recognizing that even this year there was a 30% increase in the cost of natural gas. So there are real costs occurring with the existing infrastructure that having an all-electric system that has tremendously high efficiencies is going to pay back over time. So sorry, not a right exact here's your number answer because it is really complicated, but hopefully that answered your question. Oh, and the question was, did I say the question?
You're fine. You're fine.
All right.
You're doing
Trying.
a great job. Let's do a couple more. There's one right here.
Yeah. What? You called somebody.
Walter?
Oh, okay, so what's the cost of ownership of the system compared to something else that would heat and cool water on campus? Like over the next 25 years, are there parts that degrade, parts that break down at the same rate as the existing steam plant, or is it different? Is it?
Yeah, so we actually, as part of this project, we toured some other facilities that have these on a smaller scale, and from their experience, there's a learning curve. It's just different technology. Heat pumps are different than what some building owners run, which are gas-fired boilers, whether that's a hot water boiler or a steam boiler. But their philosophy and what they've seen in their building is that after that first year learning curve, there was no additional, there was no difference in maintenance of the building using geothermal than there was of the building using a gas boiler. And the energy efficiency of that building was so exciting and so beneficial to the university that they're looking at doing it more and turning to CWU and what they're doing here and looking at putting in more of the eco-district approach to serve a greater community of buildings. So it's different initially, and that is part of the equation is bringing on staff that will learn this technology, but this is largely where the future is going, and so it may be that this is the new standard technology that people become familiar with.
Here's the last one.
I'm a historian, so I'm very curious about how long will this energy system, how long is it supposed to last? How long are buildings being made to last now? What is the lifespan? Because, as you said, there's a lot of carbon involved in the actual construction. So
yeah, so the question is, what is the lifespan of this system in buildings anymore? Because this is maybe a newer technology. So, well, first I'll say heat pumps are not a newer technology. They've been around for many decades. There were a lot of problems with them in the 90s and early 2000s that have engineering and design has really kind of overcome a lot of those. Buildings in general, Washington State, and especially on college campuses, are built for at least 50 years. And if you walk around campuses, you can see buildings are built and used for 100 years. Buildings are not are not intended, especially at the university level, to be, let's tear it down in 2 years. They are meant to be a landmark and used and renovated. And that's where, when we looked at that energy roadmap, that was a lot of the decisions that maybe we didn't pick a system that could have lowered our EUI a little more, but what it did is reduce the flexibility long term to use the building for different purposes. Because it is possible that in 30 years, maybe that's a science building. Maybe it's something completely different. So we have to be thoughtful, and that's where the design team was very thoughtful in what systems were put into the building to allow that future flexibility and ensure this building is around for 100 years.
Let's thank Anthony one more time.
Thank you, everybody.
Thanks to Susan Kaspari for arranging to bring our speaker in. You've got options. Room 116 for a master's thesis defense. Room 206 for alumni reports. Or Vindman's Bakery. Those are your three options. Thank you for coming.
Yeah, for sure. Yeah. Cool. You're welcome.
Oh, so I'm going to grab this right off of you here. Excellent job. Excellent job. Hey, John. Hi.
That was nice.
That was a good one, wasn't it? Yeah. Okay. Thank you for joining us today. Very different kind of a talk for this series. Hope that you enjoyed it. We're going to take a few Fridays off. If you're a fan of this series, we won't be doing this again until the last Friday in March. And the reason for that is it's final exams coming up in a couple of weeks, and then there's spring break vacation for everyone. And we will start the spring quarter here at Central Washington University the last week of March. So the last week of March, the last Friday, I don't know what the date is, but it's the last Friday of March is Harold Tobin from the University of Washington. And he will be over here giving an earthquake talk. And then the rest of the spring, Hannah and I put the schedule together. Off the top of my head, we have kind of a teacher education talk. We have a Carl Loquist at Central Washington University is retiring, and I saw him here today. So he'll be giving a talk on rock glaciers and maybe talking a little bit about the history of the geography department here at Central through the years. Couple other talks, I can't remember what they are at the moment, but thank you for joining us for this one. And I don't think I will be live streaming at all for the next few weeks. I enjoyed doing the Google Earth by Glenn interview, which was not live, but a recorded Zoom interview. I liked that, and I have a few others planned with some people that you know and some people that you don't know. And so I need to start thinking seriously about the downtown geology lectures, the 3 Brett's lectures coming in early April, but I haven't even started thinking about that yet. Okay, that's enough for now. Thanks everybody, I love you and goodbye from Ellensburg, Washington, USA. Balloons, hey. All right, okay, goodbye.
Good job, Nick.
Thank you.